The next topic is how to implement system calls. In current Pintos, system call handler table is empty. After modification, you have to fill the system call handler of Pintos, and then you have to implement system calls so that the users can use it. The system calls that need to be implemented includes health and all these functions and these functions. You're going to get into details with integer functions later. System call is a programming interface for services provided by the operating system. It allows the user mode programs to use kernel features such as creating a process, accessing a file, saving a file, and stuff like that. System calls run on the kernel mode. We have dealt with the instruction int in detail and what kind of parameters are passed from user mode to kernel mode. The key point of system call is that the priority of execution mode is raised to the special mode by generating hardware interrupts. So from the user program, if you want to use a kernel service such as creating a process or saving a file, then you call a system call and ask for operating system to do the jobs for you. And then after system call is complete, it returns to the user mode. The important thing is from here to here, the privilege level goes up. This is the call process of system call in Pintos operating system. If the user calls a write, then there is a file, it says call.c, and then it contains a body of write. And it returns via calling syscall3. And in syscall3, it means that it is a system call with 3 parameters. So it pushes 3 parameters and then pushes the parameter numbers, and then it generates interrupt with 0630. In Pintos, 0630 corresponds to the interrupt number that represents system core. And here, if you look at interrupt 0630, there is an interrupt handler for this interrupt. And then there is a body called syscall_handler. And that function is currently empty. So to implement a system call, you have to fill this out. Eventually, you have to fill the system call handler with this function, like this. And then each system call has its own number. The system call number is defined in syscall_number.h. For example, in our system call handler table, syshealth, the health system call corresponds to system call number 0. Exit system call has system call number 1 and stuff like that. Let me explain the requirement for system call handler. First, you have to make the system call handler to call system call using system call number. And the most important part of the system call handler is check the validation of the address the user program has supplied. Let's say this is system call, and it gets a parameter void. This is system call. And in the user program, for example, user program has called a system call with 0. Then in the system call, inside the kernel, the operating system tries to access this address. Then we won't know what is going to happen. So before calling the body of the system call, the operating system or system call handler has to check if the address supplied by the user program points to the correct address or not. So the pointers must point to the user area, not the kernel area. So this is user virtual address space, this is kernel, and this is user. And the pointer supplied by the user to the system call should point somewhere in the user address space, not in the kernel address space. And If these pointers don't point to the valid address, the page fault should occur. And then once the address validation completes, then it copies the argument in the user stack to the kernel. And then after that, it saves the return value of the system call at EAX register. So the important thing is that user should supply the valid user address to the kernel, and then the kernel should not access user's address space while it is executing. Instead, it has to copy whatever the parameters are to its own address space from here to here, so that kernel can execute the program inside the kernel without accessing the user address space. User can pass invalid pointers through the system call. It can pass null pointer or pointer to the unmapped virtual memory, or it can pass the pointer that points to the kernel's virtual address space, which is above 5 base. In both cases, the operating system has to kill the program. So when a user calls system call, kernel needs to detect invalidity of pointers and terminating process without harm to the kernel or the other running processes. There are two ways to detect the validity of the address. First one, it checks the validity of the user provided pointer. So you have to check the page table, and you have to check whether a given address is mapped or not. So you have to use the functions provided in pagedr.c and vaddr.h. The other method is check if the user points to the address below 5 base. In that case, operating system does not check whether it refers to the mapped address or not. It just checks that a given user point is below 5 base. So in case user supplied pointer is invalid, then it causes page fault. So you can handle by modifying the code page fault, and this is faster because you don't have to check anything, and it relies on hardware MMU to verify the validity of the user address. So the second approach is widely used in the real operating systems such as Linux. Let's look at this example. A process can hold a lock or ask for malloc. And then in the course of performing malloc, and page fault occurs. Then the process dies, but the global variable lock is still held by the process. Or this process got a malloc, but it did not free it. So as a result, page fault may incur the leakage of the resources. So before terminating the process, the operating system has to unlock or release a lock or return the allocated memory space to avoid any kind of resource leakage. Handling this kind of resource leakage is different in method 1 and method 2. In method 1, it is straightforward because the operating system takes care of everything. So in system call, it lock or allocate the page only after verifying the validity of the pointers. But second approach is more difficult. The second method is more difficult because there is no way to return an error code from a memory access. So you can use the following functions to handle these cases. There are two functions. First one is get underbar user, and the second one is put underbar user. Get underbar user reads a byte from the specified address, and put underbar user writes 1 byte to the user specified address. These are the system calls you have to implement. In this page, there are process-related system calls. The health shut down the Pintos. Operating system Pintos should not shut down, and it should be shut down only when health is called. The second function is exit. It exits the process. When it exits the process, it should print out the name of the process and exit status. And then exec is a command that creates a child process and execute a program. It is important to note that this exec is not exec in Unix. Here, exec in Pintos is similar to fork and exec, the combination of fork and exec. Together. And wait system call is wait for a termination of child process whose process ID is PID. And in this project, you have to introduce a notion of process hierarchy. You have to specify the parent process, and you have to specify the child process it has created, and you should have a pointer to point to the siblings. So there are two concepts you have to implement. First one is parent. You have to add this field to the thread structure. First one is pointer to the parent process, and second one is pointers to the siblings. So it goes to the double linked list, and then it contains the pointers to the children. You don't have to, there are many ways to implement the pointers to the children, but it is not reasonable to install all the pointers for all child. Usually you can maintain a pointer to the tail of the siblings list and then head of the siblings list. And you can arbitrarily order the child list, but list of siblings can be maintained in the order it was created, from the oldest to the youngest. Let me explain how we implement wait system call. Wait system call wait for child process to exit, and it retrieves the child exit status. If PID process is live, it waits till it terminates, and then it returns a status that PID passes to exit. If the PID did not call exit but was terminated by the kernel, it returns -1. It is possible that parent process can call wait for a ready child terminated process, and then it returns exit status of the terminated child process. The important thing is that after the child terminates, the parent should deallocate its process descriptor. Wait fails if the process ID does not refer to a direct child of the calling process. The operating system limits the ability for a process to wait. It should wait for only its child. And the process that calls wait has already called wait on PID, then the process wait failed. So this is current form of process wait. So you have to implement it. But implementing it is not easy. So for now, you put it at infinite loop here. So that is what you are supposed to do for this project. But this is not the correct way of implementing process wait. Let me explain the correct implementation of process wait. Process wait, it searches the descriptor of the child process using the parameter, and the caller blocks until the child process exits. And once the child exits, it deallocates the descriptor of the child process and returns the exit status of the child process. So how can we synchronize the caller of process wait and the execution of the child thread it waits for its termination? It adds a semaphore wait to the thread structure, and this semaphore is initialized to 0 when the thread first created. And in wait system call, the caller calls a sema-down for the semaphore thread ID. In the exit process of TID, it calls sema-up. It increases the semaphore value by 1, and the sema-down decreases the semaphore value by 1. Because the semaphore value is initialized 0 when the first thread is created, the call for wait system call, by calling wait system call, the caller is blocked. And when the child process calls exit, because it increases the value of the semaphore by 1, the waiting process can be woken up from the sleep status and go ahead. And also in the exit, the process has to return its exit status. So we need to add a field to the structure thread to denote the exit status of the thread structure. So this is the block diagram, control flow diagram of how we add a semaphore. So we in the process wait, we call sema down. And then in exit, we call semaphore up. So by calling semaphore down, the caller blocks at this point, waiting for the child process to finish. When a user process calls exit, it calls semaphore up so that any process that has been waiting for the semaphore value to be increased is unblocked from the sleep status. Now it's the exec system core. In Pintos, exec system core is the combination of fork and exec in Unix. So exec system core in Pintos, it creates a thread and executes the binary. So exec system core in Pintos gets the command line argument, and it runs a program which executes command line. So it creates a thread and run exec in Pintos is equivalent to fork and exec in Unix. It passes the arguments to the program to be executed, and it returns process ID of the new child process. The parent process calling exec should wait till the child process is created and loads the executables completely. That's what exec system core is supposed to do. Of course, exec system core does not wait for the child process to finish. It just creates and loads the executables completely. And then the exec system call can return. Let me explain how we implement process execute. Process execute is a kernel function for exec. So parent should wait till it knows the child process is successfully created and the binary file is successfully loaded. So you're going to use semaphore to synchronize the caller and the child process that has been created as a result of calling process on the execute. We're going to use semaphore. We add a semaphore for exec to the thread structure. So now this is a second semaphore for the thread structure. This semaphore value is initialized to 0 when the first thread is created. In exec system core, in process execute system core, it calls sema down to wait for the successful load of the executable file of the child process. When executable file is successfully loaded, it calls sema up. And we need another variable that represents the load status. In the thread structure, we need a new field to represent whether the file has been successfully loaded or not. So, as a result of this is parent process, and it calls process execute. And then in the start process, it allocates a thread structure and it creates a new process. And then it loads the binary file for a program to execute. So when it becomes child process here, and then parent process has to wait until it ensures that the binary file it wants to execute is completely and successfully loaded to the memory. And then it starts to execute the program. So if you look at the control flow, parent process continues executing, and then it calls process execute, and then in the part of process execute, it calls start process. In the start process, at some point, new thread is created, and then new thread continues execution, and then it loads the file, and after it finishes loading the file, it reduces the semaphore down. And then both of these two processes can continue in parallel. So this is how you implement correctly, how you implement the exec functions. So exec, after it calls process execute, inside the process execute has to wait for sema down. And then in the start process, after it finishes loading, it calls semaphore up. So there's an important issue here. Where are we going to put the sema down function? Is it going to be right next to the process execute, or are we going to put this down inside process execute? The next function we're going to cover is exit. In exit, you have to return the exit status of a given process. So, if a process called exit, then operating system has to terminate the kernel user program and then returns the status to the kernel. And if the process parent waits for it, then it will read the exit status of the given thread. So, in the existing exit body, you have to add the code to save the exit status at the process descriptor. Okay, this is a structure thread. And then also you have to print the exit status and then name of the thread. And then you call thread exit. So this is kernel function for exit, which is thread exit. And here you have to store the status to the status of a process. And then you call semi up so that a process that has been waiting for this thread to finish can process. So this is body of exit. And then let's look at the details of the code. This is thread exit. And then it disables interrupt. You have to disable the interrupt whenever you manipulate the thread list. So, and then you remove the node from the thread list, and then you change the status of a thread from whatever to thread dying, and then you yield the CPU to auto process. And then this function is not reached.